Welcome to the Explainer. Today, we're unpacking a fascinating new framework from researchers at Oxford and other leading institutions. It's an absolute breakthrough that gives us unprecedented control inside the ultimate black box of our era, artificial intelligence. So let's kick things off with a massive question. Right now, we're dealing with these incredibly powerful multimodal AI models, systems that can read text and analyze images at the exact same time. But honestly, despite all that power, they remain deeply, deeply mysterious. If we don't fundamentally understand how they map concepts internally, how can we ever hope to safely control them? Here's our roadmap for this explainer. 1. The AI black box. 2. Introducing MMDiff. 3. The 3 steps to control. 4. Testing the framework. And 5. The future of AI. All right, jumping right into part 1, the AI black box, or as I like to call it, flying blind. Think about the latest AI systems you've interacted with. These multimodal large language models, they're amazing. They exhibit incredibly strong visual understanding. But here's the catch. The researchers building them are effectively flying blind. The internal features that actually cause the AI to recognize a dog, read a street sign, or even refuse a dangerous prompt, they are buried deep within complex neural networks. Historically, it's been insanely challenging to identify these features, let alone audit or control them. It's kind of like having a high-performance sports car, but the hood is completely welded shut. Now, usually, researchers try to peek under that hood using something called a sparse autoencoder, or SAE. These are designed to break down an AI's hidden states into directions we can actually interpret, trying to find the concept neurons, if you will. But there is a huge problem. While they do an okay job inspecting basic text models after the fact, they've historically failed to isolate what actually changes when an AI learns to process images alongside text. They just don't capture that multimodal magic, which makes them a pretty blunt instrument if you want targeted control. Which brings us to part 2, introducing MMDiff, the surgical scalpel. So if standard SAEs are basically a blunt instrument, researchers realized they needed something way more precise. Enter MMDiff. This is a multimodal model diffing framework that essentially supercharges those traditional tools. It trains multimodal SAEs and turns them into highly precise, feature-level interfaces. Think of it like combining a high-resolution MRI with a surgical scalpel. Instead of just guessing where concepts live, MMDiff gives engineers a direct, hands-on dashboard for discovering and controlling behavior. The genius of this approach is all in the diffing. Just like a code diff highlights the exact lines that changed between 2 versions of a software program, researchers applied that exact same logic to AI. By diffing a base language model against its new multimodal adapted counterpart, they can just subtract the noise. And what's left? The exact specific features that were altered by the visual training. It is a wildly elegant way to find the needle in the haystack. Let's move to part 3, 3 steps to control, isolating, and steering. How do you actually use this tool in practice? Well, the framework relies on 3 very distinct, highly logical steps: isolate, detect, and control. Let's break those down. Step 1 is feature isolation. This is the diffing process we just talked about. You take the base language model, you take the multimodal model, run them through the framework, and boom. You identify the exact cluster of features that woke up or changed when the AI learned to see. It narrows the playing field dramatically. Step 2 gets even more specific: task-specific feature detection. To figure out what a single feature actually does, researchers use something called per-token contrastive firing analysis. Now, I know that sounds like a mouthful, but it basically means they watch how the AI's internal neurons fire when it's looking at a specific concept, like, say, a stop sign, versus when it isn't. By contrasting those firing patterns token by token, they isolate the precise causal features responsible for a behavior. And then we hit step 3, the real climax here, feature-level control. Because you now know exactly which feature causes which behavior, you can manipulate it. You can causally remove the feature to make the AI essentially forget a concept. Or you can steer the feature, literally turning up the dial to make the AI hyper-focus on it. You aren't just observing the AI anymore at this point. You are literally programming its thoughts. All right, part 4, testing the framework. Let's look at the hard data. Does this theoretical surgery actually work in the real world? Well, the researchers didn't just test this on some tiny toy model. They trained multimodal SAEs across 3 major, state-of-the-art model families: LlamaMore, PalyGemma 2, and InternVL 3.5. They put these heavyweights through rigorous testing, specifically targeting visual spatial understanding, optical character recognition, or OCR, and most importantly, AI safety. So what happens if you just use MMDiff to switch a vital feature off? The results are shockingly precise. Selectively removing specific causal features degraded the target behaviors exactly as predicted. Performance on spatial tasks dropped by an average of 12%, and OCR capability dropped by 17%. But here is the crazy part. Doing this had zero impact on the model's overall visual question answering performance. These surgically removed a specific capability without causing any brain damage to the rest of the AI. And the safety implications of this? Absolutely staggering. When researchers identified and removed the specific features associated with vulnerabilities, the success rate of multimodal safety attacks dropped by a massive 24%. Just imagine being able to proactively vaccinate an AI against jailbreaks and malicious prompts just by clipping a few internal wires. That is exactly what MDMIF enables. But we don't just want to break things, we want to build better models. Conversely, when researchers deliberately steered these features, meaning they turned the dial up instead of removing them, the AI actually got smarter. They saw a 3.6% improvement in spatial accuracy and a 1.8% improvement in OCR accuracy. These are significant boosts calculated over standard baseline steering methods. We are literally reaching in and tuning the AI's intelligence. Which brings us to our final section, the future of AI, safer generations. To really grasp the real-world impact here, I want to read a quote directly from the research because it perfectly sums up this paradigm shift. These results show that multimodal SAEs can serve not only as interpretability tools, but as mechanisms for auditing, steering, and controlling MLM's behavior towards safer and more capable generations. We are finally moving way beyond just observing the black box with a flashlight. We actually have the steering wheel now. So let me leave you with this final thought. Now that we have the scalpel to surgically dissect, understand, and steer AI behavior at the feature level, how is this going to reshape the future of artificial intelligence? Will this level of control become the new global standard for auditing AI before it's released to the public? As models get infinitely more complex, tools like MMDiff might just be the most important safety net we have. Thanks for joining me on this explainer, and as always, keep questioning the black box.